So, this is your first day at work and you're excited to change the world. You walk in, and one of the first things you want to know is the architecture of your organization. Which features are offered, how they work with each other, which teams work on those features, and where do you fit in. Your teammates hand out some diagrams that everyone seems to like. Looking at this, you can identify some things that you have heard about or worked on a similar feature in the past. Everything looks great, and you decide to implement some of your cool ideas for solving long standing customer problems. But your changes are not limited to one feature, they cut across multiple teams and multiple features. This means now you have to understand some other features by going through their architecture as well. If you are a CEO, you can summon your team to explain this entire system late night. But how many times can you call such meetings? More importantly, can you retain everything that was presented? Software evolves rapidly, and everything you learn may become obsolete in a month. So, how do we learn architecture? Even if you are an old timer in your company, you cannot know all the systems across the company. So, you reach out to your managers and they ask you to set up a meeting, which results in more documentation and more meetings. Your teammates tell you system diagrams are not enough, you should also read the documentation to understand this better. So, you gather some more links, scrolling through a bunch of pages updated 4 years ago. You reach out to the authors with questions, but they left the team last year. You reach out to other team members who are as new and clueless as you are. You contact senior developers, but they are super busy, and in the end, you realize you're on your own. While this may sound gloomy, this is actually the happy path. Imagine a distributed team where everyone is in a different time zone and each step costs you a couple days of idle time. The only guide in your journey are these diagrams and partially obsolete documentation pages. Over time, you create a mental model of your company by stitching diagrams like these. Now, this is a funny situation though. When you started, you were bubbling with confidence because these diagrams made you feel like you know the system. But for your day to day work, these diagrams added very little value. Let's take a closer look at these system architecture diagrams from a usability perspective and not merely as a formality for presentation. Regardless of your role, you expect at least some of this information from each block in this diagram. What is the purpose of this component? What is the data exchanged by this component? Nature of data and associated metadata like privacy concerns and validation rules. Source of origin and components that store or transform that data. Who are the consumers and why do they use this component? What are the dependencies and why do we use that dependency? Summary of inner working of this component, like what is the order of each step. Cost of building or maintaining this component and the impact created, like revenue. Performance metrics of this component. History of this component and how it evolved with new versions. Planned release timelines and alignment with other dependencies and consumers. People or subject matter experts who can help further. Let us revisit the system diagram from Twitter. If we want to know the data exchanged at each layer, we have to find API documentation for each component. If someone asks us the average response time of a service, we need to access different metrics dashboards for each component. If you get a user complaint of, say, tweets being shadow banned, you need to dig into multiple code bases or their documentation, but you don't even know which ones. This diagram is just a read flow, and we can be fairly certain this is a highly simplified flow that ignores many components. It's almost impossible to fit the complete read and write flow in the same diagram. The sad part is that we are used to this pain. We find people, set up meetings, go through training and documentation, get access to all the portals, and make private notes for the future. But guess what? All these components are being developed in parallel, so that by the time you get a hold of things, the architecture changes and your knowledge is outdated when you need it. So we need modern solutions that can offer something diagrams and wikis cannot. Let us walk through our goals. Number one, documentation standard. How do we define good documentation without building a consensus over what should be documented to begin with? Do we really need to document data fields or should we let it be part of the code? Should we include performance metrics or should we leave that to analytics dashboards? Can we build a documentation standard instead that captures the basic structure of a programmable process? Number two, consolidation. Most teams have plenty of documentation, but the information is scattered across different boards and portals and code bases, each requiring different access rules and permissions, sometimes even barricaded by office politics. Most engineering teams, however, are realizing these silos are detrimental to their growth, and they are looking for tools that can help towards the goal. Supporting a diverse audience. Teams across an organization have different skill sets. Some are fresh grads who may not know the supposedly obvious things that experienced members do. Everyone's expectation from documentation is also different. Product managers and UX teams avoid documentation written with engineer centric views. Similarly, many engineers also cannot understand all the different analytics tools used by product teams, but they need good familiarity with business data to make good decisions. Teams assign a lower priority to documentation because it does not help them today. It is supposed to help someone from the future. And this is a tricky situation because sometimes outdated information creates more confusion than no documentation. And finally, discovery. A common learning pattern is to explore the organization widely and then go deep into areas that sound interesting. This learning strategy, however, is not aligned with the documents today that are arranged in a hierarchical fashion, which forces teams to focus on one small portion of the entire organization's architecture. Let us try to build a new solution starting with the basics. On the highest level of abstraction, any system can be treated as a computation unit that takes some input and returns an output. If you're watching this video on YouTube, the input to the watch feature is a video URL and your identity like IP address and cookies used by YouTube to show relevant ads. The output is a video and some metadata about the video. Now that is an extremely high level view. The magic within this box is part of the YouTube algorithm which executes a series of steps transforming the input to the output. One step may be pulling your watch history from a database. A second step may rank the ads fetched from the database. And third step may transcode the video based on your network speed. So we can break this box into few more components where each of the component can be further broken down in a similar fashion. Software engineering involves breaking down systems into loosely coupled components that can be developed and maintained in parallel. The goal of an optimal algorithm in each component is to maintain correctness defined by tests written as a set of inputs and outputs adhering to a contract, reduce computation cost in processing inputs from consumers, and reduce time taken for returning outputs to consumers. One of the most important challenges for a team is to decide whether to execute a computation locally or delegate it to another system while adhering to the correctness, cost, and time promised to their consumers. Delegation does not necessarily involve using a remote API or a different code base. It just means that the component is maintained separately for loose coupling. The delegator becomes a consumer and the delegatee becomes a dependency. This delegation has an impact on cost and time. If delegation happens over a network call, it adds to network latency, network costs, as well as network errors. But regardless, the consumer has to account for the cost incurred by the dependency and its performance constraints. This also means that the dependency component cannot make changes at will without consulting its consumers. But how many consumers are we talking about? Can we really account for consumers of consumers of consumers? Can we account for dependencies of dependencies of dependencies? The popular answer is that each component should take care of its immediate dependencies. This is a linear way of doing things, which is extremely slow and prone to errors not planned for. Most organizations develop in parallel, which results in a feature graph. Each node of this graph has a direct or indirect impact on other nodes. But unfortunately, most teams are misled into believing their work is limited to the features that they directly connect with. What if we could extend this model to a customizable standard which offers a scaffold to include the essentials of any software component while also allowing customization of what to document and how much to document? This is what we call a Veda module. Veda module is the basic building block that encapsulates the essence of a process as a summary. Modules are solutions that are driven by a team and defined by a business problem, also known as feature. Feature can have one or more modules that often work together to solve a problem defined by business. Module has a contract that declares data fields used as inputs and outputs to the process. Fields can have their own properties to indicate privacy, security, and validation rules. Module uses an algorithm as a summarized sequence of steps taken to solve a problem. Each step is a smaller computation unit that also accepts some input data and returns data as output, usually a subset of module contract. A step can execute business logic locally or depend on another process for computed result. Such steps, depending on other modules, are called service steps. Now, this module may be reading from the dependency or writing to the dependency for exchanging data. Next steps are executed in parallel or serial, depending on the synchronous or asynchronous nature of the service step. Steps also document metrics for latency, cost, and planning that are involved while using a dependency because these metrics constrain the design of the consumer module. The module itself has its own operational costs, planning, and risks associated with the development. And finally, just like a module has dependencies, it also has consumer modules that largely constrain how a solution is designed. What we call system architecture is just a connected group of modules as a graph. As you can imagine, this documentation graph is very similar to all the code in an organization, generally linked as libraries and APIs. Unlike code, when it comes to documentation, you don't want to document everything. Our framework helps you document just enough. If you're an engineer, you may have noticed this module is mapped very closely to code, which offers tremendous help during development. You have all the data and associated rules, dependencies, and consumers to offer context. You have an algorithm documented as a list of clear, implementable steps on day one of work. Clear goals are set for each modules in terms of timeline, cost, security, and performance, all while accounting for the dependencies. This helps everyone understand the impact created by the smallest of components in a large organization. In other words, each module has a purpose. Similar to what you see here, engineers usually break down system architecture in small chunks of code. The goal is to build solutions as libraries and services that have a single responsibility or one purpose. Various design and architecture patterns have been developed over time. Microservices are one example of this principle. While splitting code across multiple modules is considered challenging, splitting documentation across different modules is much easier and requires very little planning. We are naming this approach purpose driven modeling. Now, you may have used modeling frameworks like UML that was developed in the 90s. While UML uses the term unified in its name, it does not really aim to unify all aspects of a software component that you see here. Our purpose driven documentation framework should resonate with most readers, even if they are not from an engineering background. Now, you may be wondering what is the purpose of a documentation module, though. The answer is the same as the purpose of the underlying software solution. When we say a system is working as expected, it implies its purpose is met. For all practical purpose, a system is working fine if it returns expected outputs for a given set of inputs. In other words, the module contract and data exchanged with consumers can be used to indicate the purpose of a software module. Now, this idea may sound far too simplistic, but this is precisely how we test software systems today. As consumers of software systems, we find systems that return the expected output when we feed some input. We don't care how it works behind the scene or what side effects it has on other systems. And Veda modules, using the purpose driven modeling framework, extend the same model to documentation. Let's review some advantages of this new approach. Since Veda module is a structured summary, it helps define documentation goals across the organization. Structure makes it easier to divide the responsibilities for documenting each section of a given component. Short summaries are much easier to update than long form wikis, resulting in frequent updates, and sections not updated can be easily identified for improvement. Consolidation ensures important design factors are easily accessible, while a documentation standard helps readers from all backgrounds, be it product, engineering, or management, regardless of their experience levels. Since modules are interconnected, diagrams are weaved dynamically and therefore are side effect of documentation. Writers document their part without guessing what others do. Now imagine drawing a diagram without drawing any dependencies, just connecting to the existing ones. Readers interactively draw what they need to explore the entire organization and visualize all end to end business scenarios. This can help identify performance bottlenecks and opportunities for improvement with the right partners. This discovery process results in collaboration as a side effect because teams can now understand the constraints faced by other teams. We get all this without learning new tools for diagram creation or maintaining a separate diagram repository. Because diagrams are closely mapped to code, it makes it easier to convey requirements and understand the overall architecture without digging deep into code. As a side effect, diagrams are always in sync with documentation. This research paper on transformers is one of the most popular ones in recent times, and yet most readers did not catch the gap between documentation and the corresponding diagram. This documentation graph of structured summaries allows us to build some new documentation-centric solutions that were not possible before. We have just seen the interactive diagrams. Another solution is the field tracing tool, which allows you to trace the complete journey of a given data field from source to sink and back. Because we document field mappings across all teams and all features, field tracing works even if different teams use different names for a given data entity. You don't need to write additional code for tracing, you don't need to buy or learn new tools, and it still helps both the product and engineering teams. You may have noticed that consumers are treated as a first class citizen in these diagrams. Most teams track their dependencies because not doing so will break their system. But this need not be a one way process. Software modules also need to understand who their consumers are and what their needs are, and their needs should be reflected in the architecture decisions taken by each component. Veda modules allow you to track different versions of consumers, showing exactly why they depend on a given module. Features also evolve over time, and so do the backing design modules. It is easy to compare structured summaries for detecting changes across different versions. Modular documentation plays a big role here. Imagine keeping a bunch of system diagrams to compare and find out which components changed over time and how. Compared to the current state of documentation where teams maintain high level and low level diagrams, Veda modules can be composed to build hybrid diagrams by mixing low level and high level modules, where each step of high level algorithm can be broken down into new low level modules. Readers and not writers decide what to include in a presentation. Good decisions cannot be made in isolation. A graph of modules with varying level of details capture all the information needed for good decision making. The design factors of cost, time, and performance can be calculated in a cumulative fashion. This is an extremely difficult operation in the tabular world of Excel sheets and dashboards that we currently live in. All this talk does not really matter if teams do not update documentation. The corporate way of incentivizing good behavior is through monetary or social measures, but we believe good documentation can be rewarding if it regularly saves times for all the team members. One of the biggest time killers at work is the information hunting process, which requires meetings or going through hundreds of documentation pages. Team Veda is a design repository that is updated on a regular basis, just like your code repository. Tools like interactive diagrams and field tracing work best if all nodes are updated. This is what keeps all the teams invested in collaboratively keeping the documentation up to date, almost like a relay race. Because the entire graph is accessible to leaders and executives for self exploration, there is a strong visibility for all the participants, and everyone understands the mission that they are working towards. We hope this introduction helps you get started. We also have an exhaustive documentation for details not covered in this video. For any questions or feedback, please use our social media channels linked in the description. Thank you for joining us.